Keyword intro reveal, Margaret Hamilton. In 1968, a young mathematician named Margaret Hamilton wrote an internal memo at the MIT Instrumentation Laboratory. The memo proposed a new term for a new discipline that the people who build complex software systems would need to call themselves something. She suggested software engineer. The proposal was, at the time, considered slightly absurd. Engineering was a thing you did with bridges and aircraft. Software was lines of code. Calling someone who wrote code an engineer was, in 1968, dignifying a craft with a name it had not earned. A year later, in July of 1969, the code that Margaret Hamilton's team had written landed 2 men on the moon, gracefully recovering from 4 computer overloads in the final 2,000 meters of descent. The term after that stopped being absurd. This is the slow story of how she got there. Settle in. Margaret Heffield was born in 1936 in Powley, Indiana, a small town on the eastern edge of the Corn Belt. Her father was a philosopher, her mother a homemaker. She read constantly and was, by her own later account, the kind of child who would do mathematics for fun. She studied mathematics at Earlham College, a small Quaker liberal arts school in Richmond, Indiana, and graduated in 1958 with a bachelor's degree. She had taken every mathematics course the college offered, and several that she had asked the faculty to invent for her. She had married, at the age of 20, a man named James Hamilton, who was about to begin law school. In 1959, she moved with him to Boston, where he had been accepted at Harvard Law. She took a job, intended to be temporary, in the meteorology department at MIT, working as a programmer for a man named Edward Lorenz, the mathematician who would, several years later, accidentally discover chaos theory while running a weather simulation on the same computer that Hamilton was learning to operate. This was 1959. The discipline of computer programming was less than a decade old. There were no degree programs in it. There were almost no textbooks. There was no software industry. A programmer was someone who, by trial and error and a willingness to read assembly language, could persuade the room-sized machines of the late 1950s to do useful work. Hamilton was, by all accounts, very good at this almost immediately. Lorenz remembered her as the only programmer in his lab whose code worked the first time. In 1961, Hamilton moved from the meteorology department to the MIT Lincoln Laboratory, where she joined a team working on a project called SAGE, the Semi-Automatic Ground Environment, the air defense computer network that the United States had built during the 1950s to detect Soviet bombers approaching North America. SAGE was, in 1961, the largest software system in the world. It ran on 22 enormous IBM computers, each of which occupied an entire building. The code was written in assembly language, by hand, by a few hundred programmers scattered across half a dozen sites. Hamilton's specific job at Lincoln was to debug the code that other programmers had written and that, when run, was producing results that did not match what the customer, the US Air Force, expected. She became known in the small community of SAGE programmers as the person you sent the impossible bugs to. The bugs that nobody could reproduce. The bugs that only happened when the system was under live load. The bugs that, by their very nature, were not failures of a single line of code, but failures of how the lines worked together. It was at Lincoln that Hamilton began to develop the intuition that, several years later, would become the foundation of the discipline she named. The intuition was this: software systems, once they exceed a certain size, fail in ways that are not the fault of any individual programmer. They fail because of the architecture of how the parts fit together. The discipline of writing them must therefore be a discipline of design, of anticipating, before the code is written, the conditions under which the parts will be asked to work together, and of building in defenses against the cases the parts cannot handle. In In 1964, Hamilton was offered a position at the MIT Instrumentation Laboratory, 3 buildings down Main Street from the Lincoln Lab. The Instrumentation Lab had recently signed a contract with NASA to design the guidance computer for a program called Apollo. She accepted. By 1965, Hamilton was leading the onboard flight software group at the Instrumentation Lab. She had by then about 100 programmers under her direction. They were responsible for every line of code that would run on the Apollo guidance computer during a mission, from launch through translunar coast, through lunar descent, ascent, rendezvous, and Earth return. The team was, in its composition, unusual for 1965. About a third of the programmers were women, a much higher proportion than in commercial software work of the era, because the MIT Instrumentation Laboratory's hiring criteria for programmers in the early 1960s had been entirely meritocratic. The lab had not particularly cared whether its programmers had degrees, what college they had attended, or what gender they were. It had cared whether they could, when given a difficult problem, produce code that worked. Hamilton's day-to-day work on Apollo was managerial in its form, but technical in its substance. She reviewed code. She designed system architectures. She wrote the requirements, documents that described what the software was supposed to do. She wrote the testing protocols that determined whether the software was doing what the requirements said. She negotiated, often heatedly, with the hardware team about which functions should be implemented in software and which in hardware. She also, periodically, made decisions about the architecture of the onboard software that, in 1965 and 66, were considered controversial by senior people in the lab. The most consequential of these decisions was her insistence that the onboard software include an asynchronous task scheduler, a piece of software that could prioritize tasks in real time, drop low-priority work gracefully when the computer was overloaded, and continue performing the high-priority work without crashing. Several senior engineers at the Instrumentation Lab thought this was overkill. The lunar module's computer, they argued, was a small, well-defined system. It would always know exactly how much work it had to do. It would never be overloaded. The asynchronous scheduler was an unnecessary complication. Hamilton argued back that this kind of reasoning, that the system would never encounter the edge case, was the kind of reasoning that produced systems that failed. She argued that the cost of including the scheduler now was small. The cost of not including it and discovering, during a manned lunar landing, that the computer had crashed because it was overloaded was incalculable. She won the argument. The scheduler was included. Four years later, at 12 minutes and 33 seconds past 9 on the 20th of July 1969, with the lunar module 2,000 meters above the surface of the moon, the Apollo guidance computer was overloaded by a switched-on rendezvous radar. The asynchronous scheduler dropped the radar task. The descent guidance continued. It is fairly often said that this is the moment that proved Hamilton's career. It is more accurate to say that this is the moment that her career, already proven, became visible to people outside the laboratory. Margaret Hamilton left the MIT Instrumentation Laboratory in 1976, 12 years after she joined it. She founded a software engineering company. She continued, for the next 4 decades, to refine the discipline she had named. In 2016, at the age of 80, she received the Presidential Medal of Freedom from Barack Obama at a ceremony in the East Room of the White House. The citation described her as a pioneer in software engineering. The phrase software engineering had, by 2016, been in continuous use for 48 years. The discipline employed worldwide about 25 million people. The vast majority of them had no idea where the term came from. They had absorbed it the way one absorbs any term that has, by the time one encounters it, simply become the name of a thing. the thing it named. The discipline of designing systems of code that work reliably under conditions their designers cannot fully anticipate has, since 1968, become the central engineering discipline of the modern world. It runs the banking system. It runs the air traffic control system. It runs the power grid. It is, in 2026, the thing that most cleanly separates the modern technological civilization from every previous civilization that has existed. The thing was named into being by a young woman writing an internal memo at MIT in 1968 because she wanted her work to be taken seriously by the men around her. That is the small, quiet thought to fall asleep on. Disciplines are sometimes named into existence by people who notice, before anyone else, that what they're doing needs a name. The naming is often the first work of the discipline. It is often the most important work. And it is often the work that is most quickly forgotten. Sleep well. Sleep well.